In this video, we're going to use this involute spur gear generator to generate uh, two gears that could be used at an intermediate stage in a two-stage transmission. And then we'll go over how to um, join them together in a single part. And then also how you might, if you need to make some small adjustments for 3D printing, how you could do that as well. And then we'll look at a couple of different bearings and ways that you might support the gear. So when you open the involute spur gear generator, which is available on the Canvas site, you get this gear right here. So suppose maybe we want to have like a 20 tooth and a 60 tooth, and we want to put them, be able to print them just as a single part, so that we don't have to worry about how to transmit the torque from one gear to the other gear. So first of all, let's make the 60 tooth gear. So to do that, we can just right click on equations, select manage equations, and we'll use the same diametral pitch as the Vex gears. So that's just 24, which just means that there's 24 teeth per inch of diameter. And then we'll say that we'll make this a 60 tooth gear. And typical pressure angle, the pressure angle for the Vex gears is 20, and that's a very common pressure angle. I don't think in most catalogs I've seen 25, so I'm not sure where that comes from. So anyways, let's look what we have at this point. We have diametral pitch of 24, 60 teeth, and a pressure angle of 20 degrees. Okay, so there's our 60 tooth gear. Now this gear comes with this hole pattern here. You can see that's a certain center hole, and then you have this other hole pattern here. And maybe we're not going to use that, so I'm just going to, excuse me, rather than deleting it, I'll just suppress it for now. So one thing you could do, suppose you wanted to have this hole be the same size as, let's see, let me see if I think I have this open. You know, a Vex flat bearing, right? So this is a bearing that can be used with the 1/8 inch square shafts or with an 832 bolt, right? So I click on that, and that says 0.17. So let me just, okay, so I'm just going to change this to 3 decimal place precision here. In inches, a lot of times you want to do 3 decimal place precision, because in a machine shop, generally on a milling machine that's well calibrated, you can hold about 1/1000th of an inch. So anyways, if I click on this, you can see it's 0.167. So we might want to go ahead and make the center hole here, right? So if I just click on that and make that 0.167. Okay. Right now, the way this file comes in, you have the dimension name is turned on, so we don't really need that. I'm going to turn that off. And then it's also set to show dimensions both in inches and millimeters. And so I'm going to go to settings again and document dimensions and turn off the dual dimension display. Okay, so this, you know, again, depending on how your printer is calibrated, you should be able to put like an 832 bolt through there and use that as an axle if you wanted to. If you wanted to do the square, so I think what I'll do in that case is I'm just going to suppress that hole and we'll throw a sketch plane on here and use the center rectangle. Okay, and then we'll just hold down the control key to multi-select and make those equal. And then maybe just, what I found on my printer is if I make this 0.127, so an eighth of an inch is 0.125, right? So if I offset it 1/1000th of an inch, then of course the overall distance from side to side is going to change to 0.127 inches. And on my printer, it seems if I do that, then I get a snug fit with the Vex square axle. So anyways, I'll go with that, and then I'll just do a cut and do a through all. Okay, so now we have a hole, and so this part of the gear is set. And what I want to do now is give it a descriptive name. So I actually should have done this first. In other words, this original part here, we want to just leave as our kind of our template for making gears. And so I'll do a save as and put it in the same folder. But I want to give it a descriptive name so I know that it's my gear, and I know have some information about it. So I'm going to call it MB spur gear, and then say this is what, 60 tooth gear, and then we'll say the diametral pitch is 24, and then I'll put in PA for pressure angle is 20. Okay, so that way I have a title that tells me what it is: 60 tooth gear with a diametral pitch of 24 and a pressure angle of 20 degrees. So that's the first gear, and now let's make the 20 tooth gear. So to make the 20 tooth gear, I can just do a save as, and then all I have to do is change that 6 to a 2, right? So now it's a new part. It's called 20 tooth, and of course I just have to go to manage equations, and under number of teeth, I'll just change that to 20. Okay, and I'll hit regenerate, so that should put in the rest of the teeth. So now I have a 20 tooth and a 60 tooth gear. I'll hit save on that, and you can see that's still it's a 0.127 by 0.127 square hole there. So now I'll go ahead and open this 60 tooth. Okay, so I'll have the 20 tooth gear part open, and the 20 and the 60 open. And now I'll do a new inch assembly. Okay, and I'm just going to pin this. And so first I'll bring in the 60 tooth into the assembly, and instead of left clicking to place it, if I hit enter and then hit enter again, it lines up the origin of the gear with the origin of the assembly, and the right plane with the right plane, and so on. And then I'll just bring in the 20 tooth and just put this over here, and that's all I need for now. Okay, and so now I'll just constrain these together. So I'll pick that face and hold down the control key, pick that face. Okay, so now those are constrained together, and I'm going to turn on the temporary axes here. right, and click on that axis, hold down the control key, and that way have both the center axis of the gears line coincident. So we're all set there. So anyways, we have two parts now, and if we want to make this just a single part, I'm going to turn off the visibility on those axes. But before we do that, let's do a save, right? We want to save the assembly. And again, I'd probably want to give this some descriptive title. So I might call it NB 20 tooth, 60 tooth. I could give it the rest of it as well. Diametral pitch of 24, pressure angle 20, and I might even say square hole, and I'll just make it say 127 for 127 thousandths. So that way, again, have some information about what we're doing here. Okay, so we've named the assembly. Now what I want to do is join these two parts together. So to do that, there's different ways that you can do this, right? But the way that I'm going to do it, whoops, is fly that out and select new part. For some reason, it's not liking my templates, so I'm just going to ignore that. Okay, so now we've created a new part that at this point is just virtual in the assembly, right? If I go to my internet, my files explorer rather, and just show you that, you can see I've got the two gears I've created in the assembly, right? But no third part is there yet. Okay, so now what I'm going to do is just right click on the new part and select edit part. And then I'll go to insert features and select join. So hopefully you could see that on the video. And now we got to select the parts to join. So I'll select the small gear and the big gear and click on the green check mark. Okay, so now, and I'll just get out of that part. And so now we have this new part that's been created from these other two parts. Notice that the other two parts, the visibility is turned off now. And this part still doesn't actually exist outside of the assembly. So again, if I click on this, you can see there's the assembly, but there's no other part there. Okay, so at this point, this is just virtual, so it's part of the assembly. It's not its own, part that I could create an STL of. And so what I'm going to do now is I'll hit save, and I get this dialog box here. So I'll say save all, and then I get this box right here which says save internally. So that in other words, it would be a virtual part inside the assembly. I can say save externally. So that's what I'm going to do. I'll select save externally and pick on the part, and it wants to know what the path, where to put it. So I'm going to say put it in the same folder as the assembly and select OK. Okay, so now if I look in the folder, right, here's the part right here that we just created, right? So in other words, we have the assembly, we have the two gears we created, and here's the new part. Okay, and right now it's just called part one. I can change that. You'll also notice that you have these arrows here, and let's look at what that means. That means that it was created from these other parts, and if I click on, and, oh, by the way, you can see that I could go back to making it virtual rather than being its own separate existing part. I could just make it virtual inside the assembly. But let's look at this external references. So now you can see that this part, right, part one, it was created with these two other parts that were held in context by assembly constraints. All right, so what does that mean? Well, or is that a good thing or not? Or there's a break all command. I could break the references to these other parts if I want to. So at this point, even though it's a separate part, right, and as we saw in the, it exists in that folder, it's still connected to the parts in this assembly. So suppose I change one of the parts in the assembly, like suppose I say, well, for the 20-tooth gear, suppose I decide, well, I really want that to be a 12-tooth gear, right? So click on Manage Equations, and instead of having 20 teeth, we'll make it have 12 teeth, and say, okay. All right, so now it's a 12-tooth gear, and I'm just going to save that. It's a 12-tooth gear, and if I go back to the assembly, you can see that that's now a 12-tooth gear. And by the way, let me just show you something. I could turn off the visibility of that part and turn on the visibility of the other two, right? And you can see that, I'll turn this one back on, right? That there's still, that in other words, the new part, part one, has changed. Because we changed the 20-tooth to a 12-tooth, it's changed. I'll just turn this visibility off. Okay, now what about if we look at the, and I'll just go ahead and save that. Okay, and let's look at, let's see, I think we have to open it, right? It's not actually even open. So let's open part one, see what that looks like. All right, and you can see that there's the 12th tooth, right? So it was changed. It was still connected to the assembly and to those other parts. And these arrows again mean that it's constrained to something else. It was when it was created, it was there were constraints there. So suppose we say, well, at this point, we want this to be independent of the other parts. So when in doubt, right click, right, and if you click on external, see it's still in context with these other parts, the 60 tooth and the 20 tooth. And now I'm going to say break all. I get this message saying, you know, if you permanently break this, you can't put them back, right? You cannot activate external references after they're broken. So I'll say, okay. And now those references are broken, right? And I'll save this part. All right. And now let's go back to the 20 tooth. And let's say we decided we want to put that back to 20 teeth. Okay, so now that's back to 20 teeth. If we go to the assembly, right, there's the only part we have the visibility turned on is part one, right? And if I hit the update button there, still 12 teeth on that one, right? So in other words, this part is now an independent part. That X means that the reference connection has been broken, right? So the X means that it's broken. It's no longer connected. It's its own independent part. And if I turn on the visibility, say of the 20 tooth, right, you can see there's the 20 tooth, right, and there's this part. So now, and then if we look at part one, again, as expected, right, the X means the links are broken, and this is its own independent part. So at this point, I'm just going to close everything, close these parts. You can save that, doesn't really matter. All right, we don't need that either. All right, and so now, right, we created the assembly. We created the 60-tooth gear. It's right there, right? We created the 20-tooth gear, and I'm just going to delete all those, right? So now this was the original gear generator template, and here's the part. And again, I could call this anything I want. I think we made it 60 tooth, 12 tooth, diametral pitch, 24, pressure angle, 20 degrees, and we'll say square hole 127. So I think that's fairly descriptive title of that part, okay? And then if we open up that part, okay, there it is, a 12 tooth, 60 tooth, right? The other, we've actually deleted the assembly and those other parts. That's up to you if you want to do that or not. I mean, it's the problem here is, of course, is we can't change the number of teeth there anymore. In other words, we're not connected back to that gear generating um, equations, and so this part is what it is at this point. So if we had left the references connected, then we would be able to change the number of teeth on either gear and either part. Um, but you may decide that once you know what you want, you're not going to change it anymore, and you just want it to exist as a single part and not connected with an assembly and a bunch of other parts, or the other two parts. So that's up to you. Okay. So anyways, we have this part, and if we wanted to, um, right, if we wanted to create an STL file so that we could bring it into Cure or some other slicing package, you can just do a save as, right, and fly this out, select STL. Okay, so now you have an STL of that part, and there's the STL. So that would be ready. You could bring it in and slice it and print the part at this point. Okay, now suppose we decide that and this will depend on the kind of printer you have. Like I have an Ender 3 Pro. If you're using the Ultimaker or some other printer, um, a lot of the slicing software now you can control some offsets. In other words, if you have a contour on the outside and you want to offset that a little bit, you can. So it would depend on what software you have and how well your printer is calibrated and whatnot. You generally don't want to do a scale because the scale will change everything, right? In other words, if you say, "Oh, my outside teeth are a little too big, I'm getting a little binding, so I'm going to make it 99%," something like that. Well, the outer teeth are going to move by more than the inner teeth, right? Because the distance out, say, from the center to those teeth, if you do 99% of that distance to the outer teeth, that's a different distance than to the inner teeth. And then the size of the hole, if you shrink that down, that's going to shrink the hole here. So a lot of times what you want to do is just use the offset command. So suppose I decide that I want to take, when I printed on my Ender 3 Pro, I took 1/1000th of an inch off the outside teeth there. So let's look at how we might do that. Okay, so what I'm going to do is put a sketch plane on here. Okay, and I'm just going to right click on this edge and select loop. Okay, and right now, whoops, let me try that again. Select loop. Okay, if I click on that, try that one more time. Let's see. Select loop. Okay, usually if you click on this, you have a choice of whether you want to do, loop around this face that's perpendicular to what my viewpoint right here. There we go. So that's actually going into the screen. I click on that again. So now it's the loop that's going all the way around. So what I want to do at this point is I'll click on this offset command. All right. And suppose I just want to move that, as I said, 1/1000th of an inch. Okay, so 1/1000th of an inch, but right now it's on the wrong side, so I'll just click reverse. Now it's on the correct side. Okay, and I'll click accept that. And again, there's a lot of teeth here, so it takes SolidWorks a few seconds to generate this. Okay, so now you can see, here's the dimension. Oh, and that's saying 0.001. So again, this I was using this was all originally generated from that gear generator. So depending on what settings they had, it should be 1/1000th of an inch, but so my guess is that it's just not, the resolution isn't just set. So let's go to here and we'll go to document properties and dimensions. Yeah, primary dimensions, 2 decimal places. Let's set that to 3. All right, so now we can see that that's 1/1000th of an inch. So at this point, if we do a cut, we can take 1/1000th of an inch off. And so let's go ahead and just select cut. All right, and if it looks like it's cutting on the wrong side, so I can just check this box here, flip side the cut. All right, and I want you to be able to see like how much it takes off. So normally I would just switch this to through all, but I'll just take it like that. Okay, so now you can see how much that took off. So let me just do this front view here. Yeah, so you can see, I mean, it's not a whole lot. It's 1/1000th of an inch, but I found that works pretty well on my Ender 3. If you wanted to do 3,000, so just to give you an idea, a piece of paper is 4/1000th of an inch, right? Standard piece of paper is 4/1000th of an inch thick. So this is, I just took 1/1000th off. So maybe if we wanted to do 3, right? If I fly this out and click on the sketch, there's a dimension there. So I'll make that 0.003. Okay, so now that's 3/1000th of an inch off. Again, the more if you take off too much, obviously you're making the tooth a little narrower. It's it's going to weaken the tooth a little bit. 3/1000 is probably okay. But anyways, so you can see that if you need to adjust that, and again, I would just go back to the extrude and do a through all to make it go all the way through. But that's an easy way to adjust it so that it 3D prints just the way you want it. And of course, for your model, you want it to be the correct size, not the size that's been reduced for 3D printing. So if this is when you put it back in your assembly, um, again, I could save this as the STL, but remember that I can always just click on this and hit suppress, and then it takes off. So now it's back to the regular, real the size that I actually want in the model, um, and I can always click on that and unsuppress, and it will take that amount off. Okay, so anyways, that's uh, a couple of ways that you might think about. As I said, there's other ways that you can do this, but I think this is fairly straightforward. So, so I just want to talk a little bit about some of the about bearings. So probably some of you have used McMaster-Carr before. Usually, if you order something, you get it the next day. It's there's like they have tons of different kinds of stuff. Screws, standoffs, and so one thing I just wanted to talk a little bit about is bearings and bushings. Um, so the idea here is that if you have, say, you're using a square um, Vex shaft, 1/8" square shaft, and you laser cut some birch plywood or some kind of wood, and you have a hole. You don't want to run that steel shaft, especially if it's a square shaft, even if it's a round shaft in that wood, right? So you can put like a bushing like this or some kind of bearing. And let's just look at these ball bearings here. So one type that's really nice is the flange bearing. Um, the we do have some of these ball bearings. I'll show you a picture of one in just a minute that's available in the lab that work with the 5mm screws. So in other words, you can use a 5mm screw as an axle, and we have these ball bearings um, that the ID of the bearing is such that the screw fits pretty well in it. So, but just to give you an idea, with a flange bearing, it helps line it up, right? It says ensures proper positioning inside a tube or housing. So in other words, you can press if you have a press fit and you press it into a piece of PLA or wood, then that flange keeps it lined up and also keeps it from traveling any further, right? The flange keeps it from going any further in. Um, you still might need to have a washer or something else that keeps it from kind of wiggling out over time, right? On the other hand, if you have this type, then it's a little bit trickier, right? You probably want to have like a pocket. So in other words, if you 3D print some PLA, you might want to have something that matches the OD of the bearing, but then then the inside diameter, it goes in so deep and then it decreases so that the shaft can still go through, but the bearing can't go through anymore in that direction. So these precision bearings are really nice. You don't have to get the precision ones, but so and you can also select, like, if you want to say I want to have an 1/8" shaft, and the type of bearing that you want. So you can see these are the different types. You have the outside diameter of that you press in. Then it gives you the outside diameter of the flange itself, the OD, and the thickness of the flange itself. So those are pretty nice. Another nice option is, let's see, uh, bushings. All right, so these again, they have a flange. They press in. They can have a thrust. So in other words, you can have something pushing against it in the axial direction on the other face on this, and these are generally like powdered metal with a certain amount of oil embedded in them. So they're pretty neat. These are used for things like dryer axles and things where, say you have a steel axle inside, and as that starts to spin, it draws the oil out from the powdered metal, so it's self-lubricating. And then when it stops rotating, like say your dryer shuts off or something, then the capillary action of the pores will draw the oil back into the bearing. So I mean, they're like, they're permanently lubricated bearings that last a really long time. And so those work pretty well as well. So here's just a few more things to talk about. So these are M3 and M5 screws and bolts. So one thing is we have these thread inserts, and so in PLA, of course, it's not particularly strong, but what you can do is you can, print a hole, and then you just take a soldering tip and heat it up, and then push this into the hole, and then when the PLA cools, then you have a pretty good. I mean, it's not like you have a tapped hole in a piece of steel or something, but it's a lot stronger than just trying to put the screw right into the PLA. So we have these both for the M5s and the M3s. And the other thing, just to mention here is this is what I was talking about with these bearings. So you can 3D when you 3D print, say, a gear or something like or a link, you can create a pocket and then press this bearing in, and then use an M5 as an axle, right? So these bearings work really well with the M5 screws. So anyways, that's just a few ideas that you might want to use.